Very easy to understand. It has very few degrees of freedom. Yet it has all the richness of symmetry breaking and Goldstone modes and even the Anderson-Hayes mechanism. So let me just start. So this is what you see when you see a Nematic, right? And so the dark lines are from the Greek, or the word Nema is dark lines. That's what you see. And the first thing you see when you look at a Nematic under cross polarizers is you see these spots. Right? You see these places where there are these brushes that come together. You see 4 brushes coming together. Sometimes if you look harder, you can see 2 brushes coming together at a point. And you say, what are you looking at? Well, just so we're all on the same page, this is what you do. This is how experiments are done. Correct me. You know, is this correct? Even with a digital camera, right, on the other side. So you have a polarizer and an analyzer, and you have your molecules in there, and they're birefringent, and so they actually rotate the polarization of the light, right? They have the ordinary wave and the extraordinary wave. And so you take a picture, and if the molecules were isotropic, dielectrically isotropic, you would just see black because you have cross polars. So wherever you see black, it means that either they're dielectrically isotropic or that the molecules are parallel to either the polarizer or the analyzer. If they're in the direction of the polarizer or the analyzer, then there's only one mode that goes through, and it stays polarized in the same direction. And when you see color or light, that means that the molecules are pointing in some other direction. And so what's neat about this is just by looking at that picture, the shearing texture, you can already deduce what must be happening now with the molecules. That was the brilliance of studying liquid crystals. When they did it more than 100 years ago, they didn't have AFM. They had no way of seeing the molecules, but they deduced that this must be what's going on. So for instance here, you might call this a +1 kind of defect. And you can see what happens if I brush out all the places where the molecules are either along the polarizer or along the analyzer. You get the 4 dark brushes. I can do here, you might say this is like an azimuthal defect, right? It goes around. Again, the brushes just paint out the same sort of texture. I can do that here. And you notice here, this you might call a -1 or a hyperbolic kind of defect. A hyperbolic defect also has 4 brushes. So here's a question. But you can only answer if you don't know the answer. Okay? Which is, how would you decide when you go to the shearing texture whether it's +1 or -1? So every time I see a 4 brushes, it means it goes through the polarizer direction twice and the analyzer direction twice. Which means the director goes around 2 pi, or -2 pi. Likewise, whenever I see a brush with 2, it goes in the polarizer direction once and the analyzer direction once. So it rotates by pi. How do I tell the sign? You know the answer. What you can do is you can rotate the polarizer and the analyzer. Okay? And the brushes will rotate with them if they're positive, and they'll rotate against the direction you're rotating if they're negative. All right? So you have to do a small dynamic experiment where you take 2 pictures. So you can do that. But let me say it in a more formal way, which I'll come back to soon. These are maps from the punctured plane. Nematics in general, map from the punctured plane to the projected line. And what I mean by that is, since it's nematic, it's a vector with 2 heads or no heads. I only care about the direction. I don't care about which way it's direction. I don't care about the vector head on it. So when I look at defects here, I'm looking at maps from, say, this plane with a hole poked in it to RP1. Okay? You can have other defects. They don't have to just be +½ ± ½, ±1. There are ±3½ defects, ±2, 5½ and you can see, right? All you need to do is count the number of brushes. 6 brushes here, 8 brushes here, 10 and here. There are 12 brushes coming out. And you can see that the far field tells you that there's a charge 3 defect of some kind. This was printed on extremely thin paper, right? So you can see through that. So that's how nematics work, and that's a standard story that when you have a vector field in the plane, so you can think of the XY model, or you can think of a nematic where n and -n are the same, you can have integer defects, and you can have half integer when you have this nematic symmetry. And we go about talking about these, and we're used to this, and it's something that you can talk about in complex analysis. You can talk about the order of the zero of a function, for instance. So now, let me try to connect that to Smetics. So I've set the stage for Nematics. These are called Disclinations, places where the angle is wrong. So let me talk about Smetics. So here you have Smetic liquid crystals. Smetic liquid crystals are layered systems. They're beautiful all by themselves because they mix geometry of surfaces, right? Classical differential geometry of surfaces. Each of these layers is a surface with the broken symmetries of a crystal. So there's a stack of layers in one direction that's crystalline, and each of the layers has its own geometry. And so then they talk to each other. So you have individual layers. So this can either be a neat system like a molecular liquid crystal, thermotropic, where there's no solvent. So in between really are hydrocarbon chains. Usually there's some sort of rigid backbone here. Or I can think of amphiphilic molecules with charged heads and oily tails. You put them in water and you get these sandwiches, these multi-layer structures when you have a high enough concentration of the amphiphiles. Now, I could go on about Landau theory about this and start talking about the elasticity and trying to understand ground states. But I look at this picture by Amici and Kadata. This is a Smetic. Right, it's under cross polarizers. There's no, what's that thing they do? Artificial color. All right, this is actually what it looks like in a microscope under cross polars. And you can see this is not anything near this ground state. Right, the Shearing texture is nothing near the Nematic ground state where all the molecules point in the same direction, but you can kind of understand it locally. There are these defects. This thing is very complicated. It points in lots of different directions. There's obviously some other kind of modulation of the molecular direction from layer to layer. And really what you want to be able to do is understand the data, not understand the system that would require experimentalists great effort to make. All right, so you want to look at that picture and say, what am I looking at here? All right, instead of asking experimentalists to make this nice layer structure. All right, and it will, we get enlightened by doing it. So we're interested in studying things that are not even that dependent on the geometry of this configuration. So we're going to be interested in the topology. Let me show you the energy, because energy is important in physics. So let me just tell you how we're going to model the system, or you can have it in the back of your head. Here you have your layers. The way we model the layers is we have a phase field, phi. Right? Phi is a function of x, y, and z. Phi is 0 is the first layer, and phi is a is the next layer, and phi is 2a is the next layer. So these are level sets of some field in space. I can now talk about a density, which is modulated by phi, right? So its phase is phi. I can talk about the unit normal vector to the surfaces. Each of the surfaces grad phi over its magnitude. If you're a slave to Landau Lifshitz, you say, oh, well, I want to write things in terms of u, the displacement field. So here I have phi is z minus u is the Eulerian displacement field. If u were 0, then I'd have a steep just layers going up like this, up the z-axis. And here I write down the elasticity theory for it. Usually, you're used to the elasticity theory where I have a term like that, B times dzu squared. Right? B is the bulk modulus, dzu squared is the compression energy. dzu we used to call the compression strain. And then I have to have some sort of bendy energy. Smetics are funny that way. There's no compression energy there's no energy for tilting them or rotating them, and there's no energy for there's no structure in the layers. The layers are supposed to be fluid, so there's no modulus in the layers. The only modulus is telling it the layers want to have a certain spacing this way. However, I showed you that picture, Nietzsche's picture, where we had these complicated textures. And those complicated textures are not ones where u is small. And I wouldn't want to just talk about small u and expand into small u. What I really want to do is I want to expand in rotationally invariant combinations of u. Because I want to be able to study large deformations. Over here the molecules are pointing this way. Over here the molecules are pointing that way. So to study the elasticity, I have to talk about something that's manifestly rotationally invariant. So, I have my field phi. Phi is nice and rotationally invariant. It turns out this compression energy, the term that you're used to, the dzu squared, is just the first lowest order term in grad phi squared minus 1. It's telling me the magnitude of grad phi would like to be 1. That means that you go 1 layer per layer as you move along the layers. Okay. The other term I can write down is the divergence of the layer normal, which is also the mean curvature of each layer. So now I can talk about the geometry of each layer. Each layer wants to be a minimal surface. It wants to be flat. Flat doesn't always mean flat. Flat can also mean flat like a potato chip. Flat. Right? So if you have a saddle, that's flat too. And here's the compression energy. Now, Dejene's insight was that this rotational invariance and gauge invariance are to lowest order the same thing. You write down the quadratic theory of the Smectic, it looks just like the London theory of a superconductor. Something's screened out, it looks very similar. But it's not true. Rotational invariance and gauge invariance are different. Okay, you can tell the difference between this chair and this chair, although this chair is equivalent to the first chair. Right? Rotations are different. Gauge transformations are redundancies in how you write the variables. Rotations are really rotations. So, let's continue. Let's see what we can do with an energy like this. And let's talk about the defects you can have in Smetics. So I already told you about disclinations and Nematics. Because Smetics are crystalline, and they have a broken translational symmetry, they have dislocations. They can have topological defects themselves. And that's why writing everything in terms of a phase field is natural. If I write down an order parameter, psi, which is a magnitude times a phase, here's the phase, phi, which I can also write as z minus u. Then the quantization condition, or the topological condition that psi is single valued, is that if I go around any closed loop and I integrate grad u around the closed loop, I get an integer multiple of the spacing. That's exactly the same quantization condition you have, say, in the vortices in a superconductor. And so, in Smetics, though, so what does it mean? You have to take your space, you remove a line from space, and then you have some sort of wrapping as you go around that line from space. Smetics enjoy two different kinds of dislocations, just like crystals do. They have edge dislocations. That's where you add an extra layer, right here. And they have screw dislocations, right, which is like a helicoid. So a screw dislocation is something you go around it once and you wind up one layer higher. Staircase. An edge dislocation, you go around once and you find yourself on a different floor. There are many buildings like this at universities. Who's ever been in a building? Right, where there's an old building and a new building are attached. I was in Bristol, and they have the best thing. They have two buildings attached like this, and a staircase in the middle. So they have an edge dislocation, a screw dislocation right next to each other. You can spend hours walking up and down the stairs, abusing yourself. If you can't sleep, you can do that, right? Okay. The nice thing, or a nice thing, is that to visualize the dislocation, you can do it with freeze fracture. Think about what you'd see if you were looking at a screw dislocation. In freeze fracture, what you see is you see a line. Here's that last step of the spiral staircase, and it just ends. Right? And so, these aren't the sharpest pictures, but here you have these steps, these flat steps. It's freeze fracture. You tear it. It tends to cleave along the layers, and those steps just end. And that means that you have a screw dislocation. And the whole edge where the step is the edge dislocation. Right? So every time you walk up a step, that's an edge dislocation you cross. And then as you go down the stairs in the spiral staircase, you're going around the screw dislocation. The other thing that distinguishes the Smetics, say, from what I'd say are internal degrees of freedom, is that as soon as you put a defect in, you've changed the geometry. So think about it in a superconductor. I put a vortex in, and I put another vortex in. And I know what that means. Here, if I put in an edge dislocation, and now you say, all right, put in a screw dislocation. What do I mean by a screw dislocation? What was the condition here that I had a screw dislocation? It was a geometric condition, that the Berger's vector was parallel to the direction of the defect. But now I have layers that are distorted. They're in some other shape. And so now when I put the next defect in, I'm not putting it into that same geometric ground state. So the difference between edge and screw is geometric and not topological. And so this distinction is also not that useful, as it turns out, or is hard to quantify away from a linear theory. In the nonlinear theory, it's hard to do. So let me see, can we do anything with a nonlinear theory? So let me just tell you about edge dislocations. In fact, for the rest of the talk, the only kind of dislocations will be edge dislocations. Here it is, that picture. And so, let me write down the energy for it. So here's the energy I wrote down. This is the London-esque theory of the energy. All right? So if you would imagine that I had some coupling grad U minus A, and I wrote the gauge field in axial gauge, and I integrated it out, I could have something like this. I have higher derivative terms. That's the bending energy. That's the screening that the director can use on the Smetic, or that, say, the gauge field does on the phase field. Here's a simple energy. I've written it to quadratic order. This is classic Landau-Lifshitz, volume 7. Volume 7? Is that the right volume? On what?
For what, yeah?
Elasticity.
Oh, gosh.
Nobody's ever read that one. No, there are 10.
It's the right volume.
It's 7. Okay, you have to remember which one's 9.
It's a great volume. It's electrodynamics continuous media.
Okay, 8. All right.
He's also read Harry Potter.
Right.
That's
So,
right. My mistake.
which one?
The electrodynamics.
It's 6, isn't it?
No, 6 is hydrodynamics.
Okay. All right. Anyhow, here's the free energy. Let me solve the problem for you of the configuration due to a single edge defect. Okay, watch. So first of all, I rewrite the energy. I rewrite the energy in this way, which I'm about to do some algebra. Okay, there I did the algebra. So I wrote the thing as a perfect square, right? The energy. Right, so if I square this, I get the first term. I square that, I get the second term. And I have this leftover piece. Right? So far, I haven't done anything, right? Except rewritten something in a different way. But then you stare at this for a while.
I need division by class. Cool.
I haven't done anything yet.
You've done an division by class.
No, that's just the cross term. Yeah. But now I'm going to do integration by parts. I'm going to notice that this term here is actually a total derivative. Well, that's great because you learn about this when you learn calculus of variations. They tell you, oh, well, surface terms are unimportant, or that is to say, surface terms don't contribute to the equations of motion, right? Or surface terms don't go to the mean field theory because they're boundary conditions. Right? So they're completely topologically decided. You make boundary conditions, the boundary conditions tell you what the U's do at infinity, and you're done. And watch that. So if you can, this is called the Bogomolny-Prasad-Summerfield decomposition. This is a total derivative, it doesn't contribute, and then if you just find solutions where this is 0, you're done. That's the absolute minimum of energy. Because the boundary conditions are fixed by topology. Right? When my father taught me the calculus of variations, remember this thing you taught? You have A and B, A and B, and you make another path and it's varying. Remember this thing?
Mm-hmm.
Yeah. Is that what you do? No. No, you actually, the boundary conditions are last. Right? You write down a differential equation and then you put the boundary conditions in. Here, you're putting the boundary conditions in at the beginning. Right? And you're actually then solving a lower order differential equation, which is also nice. Right? So it's lower order. Means you have to worry whether you can satisfy all the boundary conditions, because I don't have as many boundary conditions I'm allowed to specify. But the answer is yes, you can do that. All right, here is, say, a picture of these are layers of cholesterex, but it's the same thing. It's a Smetic layered system like so. And here's a dislocation. And what you do is you choose one SIGN in the upper half plane, and you choose a different SIGN in the lower half plane. And the defect is just a discontinuity in the boundary condition from the surface at z equals 0 minus to z equals 0 plus. So all I do is I put a little step in on the top and I put a down step on the bottom. That's the boundary condition. And then I solve the diffusion equation. And I know how to do that. Okay, and there you get the lines, and it's not too bad. For no work, it's not too bad. All right? And I know this is an absolute minimum. Right? It goes to the ground state, and so I say, see, the energy is actually topological. The energy doesn't even depend on the configurations on the inside. That's just like a superconductor kappa equals 1 over root 2, where the flux line is neither attract nor repel, and the energy just depends on how many flux lines you have. So now let me add a nonlinear term. All right, so I'm not going to go to that full nonlinear theory yet. Instead, I'm just going to write down the most relevant operators in the normalization group sense. So now I do have a nonlinear term that is relevant in 3 dimensions. It leads to anomalous elasticity in Smetics, which I won't talk about. And you try to do the same trick. First, you notice that these two guys, Brenner and Marchenko, in a brilliant insight said, well, look, you have 2 quadratic terms. How can the energy be different between the two? The ground state must be that this quadratic term is equal to that quadratic term. Because if it weren't, then this one would get smaller and compensate. So they just made this, I don't know, you could call it the Emery-Ma guess. They just made the 2 terms the same. They solved this equation going up and this equation going down, and there you go. Okay, you can solve those problems. That's not too bad either. What we realize is that this is actually also topological in nature. This solution is an inspired guess, but it's actually systematic. So again, I can complete the square. Now I have a nonlinear term. I have a surface term, A is just some vector. Divergence of A is the surface term. And then I have this extra piece. That piece is not 0. If it were 0, I would have exactly what I wanted. I would have a perfect square plus a surface term. The surface term gives me the energy based purely on the boundary conditions, and I make this 0 and I'm done. What is that extra term? It turns out that that extra term is proportional to the Gaussian curvature of the layers. So let me remind you about curvature. Okay? So when you have one of those potato chips, I mentioned this before. Here's a potato chip. You look at any particular point, although you always look at this point when you make this picture. And you draw 2 circles that are perpendicular to each other. Those are the principal directions. They have curvature. The circles are on the opposite side of the surface. And one has a positive curvature and one has a negative curvature. From these 2 curvatures, you can construct 2 invariants. One is the mean curvature, which is the average. And the other is the Gaussian curvature, which is the product. Right? And bending a piece of paper, folding a piece of paper over is changing its mean curvature. Making a spherical cap has mean and Gaussian curvature, and a saddle has 0 mean curvature and negative Gaussian curvature. The point is that when I have an edge dislocation, see, I told you it's a way where you can amalgamate geometry of each layer along with the crystalline structure this way. Each layer only bends in one direction. It doesn't bend in the direction out of the plane towards you or out of the board. So one curvature is strictly 0. One circle is infinite. That means that the Gaussian curvature always vanishes. What that means, going back to this decomposition, is that this is 0. So when the Gaussian curvature vanishes, then you actually have an EPS decomposition. And so then Brenner and Marchenko's guess is actually correct. You could ask yourself, well, if you were critical of the data and those curves, you'd say, well, I mean, they're not that good. Right? How can I really tell the difference between the linear and the nonlinear theory? Maybe this is all nonsense. But Oleg is capable of taking very high precision data. So the circles are the data. The dotted line is the linear elasticity theory. The solid line is the nonlinear elasticity theory. You say, oh, well, much better. But then you look at the dashed line. The dashed line, after all, you don't really know where the defect sits. Remember, in my solution, I encoded the defect by having a jump. But I don't know exactly where the jump is. Maybe the jump's over here, maybe it's over here. And so, if you actually shift where the jump is, then you get the dashed line. You say, well, that's pretty good. In fact, I couldn't distinguish between the dashed line and the solid line. Except, It turns out, isn't tight, that if you have, since it's many layers, and this is where the crystal part comes in, you have many layers. This is for the fourth layer. But now suppose you go to the third layer. You go to the third layer, it turns out you have to shift the linear theory by a different amount. And if you go to the fifth layer, you have to shift it by a different amount also. Whereas the nonlinear theory fits all the layers all at once. So it's that coupling between the geometry of each layer and the layers wanting to be crystalline in one direction that forces that in. It turns out, so this is work I did with Chris Santangelo, who's at the University of Massachusetts in Amherst, that in fact there's a superposition principle. The energy just depends on the boundary conditions. You can actually have much more complicated structures, and so we await the day that somebody will put 4 dislocations in and check the nonlinear theory. Now, I want to point out that the nonlinear theory, which is the dark lines, and the linear theory, which is the dashed lines, are not just quantitatively different, they're qualitatively different. Maybe they're both. They're definitely both. What I mean by that is that if we agreed that this was the first floor of the parking garage, so I'm in the nonlinear parking garage, you're in the linear parking garage, all right? We agree we're on the first floor. We start on the first floor together, and then we wander around, and we never go to another floor. Suddenly, you will discover you're on the second floor of the nonlinear. In my opinion, you've moved up to the second floor of the nonlinear parking garage, even though I think it's still the first floor. All right, they cross. And that's only going to get worse as you put more dislocations in. Just so you know, you can actually write down a fully rotationally invariant version of this theory, where now I have the layer normal and I have gradient of that phase field. This is the full mean curvature. You can write it again in this complicated BPS form. Here are these extra pieces. All I want to tell you is that there's a theorem, a very old theorem from 1903 that Minkowski proved. We generalized that theorem. He was talking about one surface. We generalized it to surfaces, many layered surfaces. And using that generalization, you actually can show exactly the same result. The punchline of all this is that there's a K here. K is the full Gaussian curvature. If the full Gaussian curvature vanishes, then you can write this purely in BPS form. And there's this surface term and that, and this term there.
Like to comment, they used the Harper Nelson formula where they separate the defects, so they have the discipline for defects. Then they interact and so forth. Plus, there are a field that's oscillate and small fluctuations around these things. So you're departing from that formulation.
Well,
what you gain?
So that formulation works in the linear elasticity, where it's linear, you can do superposition. Now, if the nonlinear terms are irrelevant, then it's okay. Long distances, everything is correct. However, in Smetic, it's not true. Smetics, the nonlinear terms are relevant in long distances. And so Smetic melting is a very, how Smetics melt remains controversial even after 40 years of being. And part of it is that it has this complicated nonlinear elasticity. So you can't simply separate the defects. Let me just say as an aside, right? The defects in Smetics, when you write the linear theory down, they interact exponentially. In the nonlinear theory, they interact parallel. So the nonlinear theory makes them completely different. Anyhow, you can do the same evolution. We did some numerics to check that that our simple approximation using only the relevant terms really doesn't differ from the exact solution. So I'm halfway through, and I told you all about edge dislocations, as if I understood them. So let me go back to edge dislocations, and I'll recall that we had disclinations. And the Smetic has orientational order and broken orientational order and broken translational order. So here are some edge dislocations. Right here are 3 of my favorite ones. These 2 are +2 edge dislocations. Here's a +1 edge dislocation. Again, these are maps from the punctured plane to the circle. The circle is the phase field. After all, the layers in layer +1 gives you exactly the same structure, because I'm thinking of this as a density wave. This is +2. I go around once. This is the Berger's circuit, and I've added 2 layers. Here I've done the same thing. It's a slightly different looking to +2 defect, but there it is, 2 extra layers. Here I'm adding 1 extra layer. So let's think about how we study topological defects. And we recall Merman's landmark 1980 review article in Reviews of Modern Physics, where he talked about topological defects in what is material. And we say, oh, well, we need to calculate or find the ground state manifold. Right? You look at the ground state manifold, and topological defects are closed paths, non-trivial closed paths of the ground state manifold. So, here we go. Here's phi. Phi is the shift field. All right? Like I said, I can shift and come back. It's exactly the same system. So when I shift, I can shift up to a distance A. A is the layer spacing. After I shift by distance A, I come back to where I started. So one direction of the ground state manifold is the shift, and they are equivalent to each other. But then there's another direction, which is the rotation. And I can rotate the Smetic, and any orientation of the Smetic is just as good as any other. And I can rotate it from 0 to pi. The pi is because of the up-down symmetry. Right? So I rotate from 0 to pi, and I get back to where I started. But now I have to sort of tie that whole thing up together. And when you think about it, these two lines are the same. So shifting by A and then rotating is the same as not shifting and rotating. But if I rotate first and then shift, now the shift is in the opposite direction. Shift, rotate, rotate, shift, don't commute. And so this is the Klein Bottle, Hatsutasi, okay? It's very exciting. There's the shift direction, there's the flip direction, like so on. And I identify the edges in this funny way. And you think, wow, there's going to be something hard about Smetics because of this. Right? The Klein Bottle is complicated. You notice it has a funny feature. If I flip and then I shift backwards and then I flip backwards, I actually get a positive shift. Right? So it's non-abelian. And so now I have maps from the punctured plane to the Klein Bottle. And you say, oh, this is very complicated. In particular, the Klein Bottle isn't nice in any nice way. It's not like a group. It's complicated. But we can still make progress. We can still understand it. So here is how you study defects. This is what you're taught. If you read Merman's paper, here is my sample. It has holes in it. That's where the defects are. I look at the ground state manifold. Do you ever know what this is? Anybody?
Is that a Mobius strip?
It's 2 Mobius strips. It's a Klein bagel.
It's a Klein what?
Klein bagel.
A Klein bagel.
instead of drawing the Klein bottle the way that you do, or the way that Clifford, that guy who makes Acme Klein bottles does it, instead you imagine a circle, but you twist it. So now it's a figure 8, and you ignore the fact that it crosses itself.
Okay.
And then what you do is you make it into a Mobius strip. And so that inverts the orientation of the figure 8 as you go around. And so that is the Klein bottle. And what you do is you look at paths, closed paths in the sample, and you look at maps to closed paths in the ground state manifold, and those maps are precisely the homotopy classes. Right? They give you the maps. Here, for instance, is the group structure of the ground state manifold. Here's a presentation of the group. It's the free group on shifts and flips with this funny non-abelian factor. What do you do in practice? In practice, what you actually do is you take one defect loop. You don't study all the possible closed paths here. You say, I'm just going to go around one pole. And then what I'm going to do is I'm going to look at equivalence classes of the fundamental group of that. Oops. So what do I mean by that? I mean to say, I have a closed path here, and I look at a closed path over here, but any closed path that's the same as that closed path is the same defect. If I take that closed loop around the Klein bagel and slide it around, that's the same defect. Right? As long as I don't cut that line, I'm okay. As long as I don't cut the line or cut the bagel, I'm okay. So, this leads to a lot of interesting things that are not, well, they bothered me when I first learned them. And, for instance, look at this structure over here, structure A. So here I have a structure where I have a disclination. That's one of those rotations by pi, right? Over here, up on top, the layers are all pointing up. as I go around this particular defect, the layer direction slowly rotates by pi as I go around that half disclination. Near that half disclination, I can make a dislocation pair. See, there's a dislocation pair. Just by locally cutting this out and replacing it, say, with nice flat layers, I get the same thing back. So far away, the far field is the same as this far field, which is just one disclination. Agreed? Yes? But suppose instead I take this dislocation and I pull it around the disclination to the other side. Right now I'm allowed to move the dislocations through. Right? There's no problem with that. And so I can actually, when I'm done, have two dislocations. I can actually create a dislocation pair from nothing when I have a disclination present. So that's weird. Part of the weirdness of that is because the Klein Bottle isn't abelian, and you can't talk about defect just by looking at them locally. The defect structure, the defect charge is something that's global, which is what defects are supposed to be. Right? So you have to see all the defects. So when you have one disclination there, one half disclination, suddenly you can create pairs out of nothing, or you can destroy pairs from nothing. So you can go from, and if you check the math, if you're into checking the math, it turns out that these two structures are related by conjugation, which means they're in the same equivalence class. This is not an important fact, other than saying that the mathematics is all consistent. So the first thing we learned is that when you have disclinations and dislocations, it's not so simple. They mix together in some complicated way. And you have to worry about the topology of the order parameter space.
Well, the disclinations, the extra disclinations, they should add up to the same topological charge.
These two are in the same topological equivalence class.
And this is what, half?
This is a half disclination or a half disclination with a charge to dislocation are in the same equivalence class. They're topologically equivalent. I just showed you that. I can smoothly go from one to the other. But that's what the math represents. So it turns out that there's something more to Smetics, which was even more bothersome, which is there's a theorem that we didn't understand. Oh, I guess my student understood it, but I didn't understand. By Planaro. That says, look, if you have a layered systems like Smetics can have any negative charge defect. So here's the disclination, right? So here are the layers. If you look at how the director field goes around here, right? For instance, it goes around by minus 2 pi. Here it goes around by minus pi. Here it goes around by plus pi. It turns out when you have a layered system, you can only have a defective charge plus 1. At most. It can have plus a half, plus 1, 0, and any negative charge you like. So isn't that weird? Because when I talked about disclinations at the beginning, I made this point of saying when you look under Shearing Texture, you can't tell the difference between plus or minus 3. And in Nematics, you can have plus or minus 3. But somehow in Smetics, you can't have plus or minus 3, but you can have minus 3. So there's something even wrong about the very nature of how we did the topology, because if you read all of Randall's paper, it tells you that not only if you look at closed paths on this ground state manifold, but that every closed path on the ground state manifold corresponds to some defect. And you can add defects together by doing that, and it means that I can go flip, 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 flip. That's a rotation by 4 pi, but that's not allowed. You can't have it in the layered system. So in fact, that whole story of the ground state manifold I misled you was not useful. All right? Or there was something wrong with it. Okay? There's something else wrong with it other than, besides telling you that the topology is interesting, there's something wrong with it. It's incomplete. It represents defects that aren't there. So what we realized is how do you solve this problem? Right? In other words, how do you understand the defects in a way that's mathematically consistent? And it turns out it's actually easier than studying homotopy theory, which made it happen for us. So here is my two-dimensional plane, the xy plane. See it? Here's my phase field phi. Remember I said that the layers are level sets of the phase field? Right? So here's my phase field phi of xy. How do I make level sets? I just cut it at planes. and then I project down. Right? So you cut, you cut, you cut, and you look at the projection down onto the thing. And it turns out that these lines then are exactly the lines you get when you look at a map. They're exactly the same as what you get on a topographical map. So Smetics have an extra property. They are not arbitrary lines. They are the lines that are the iso heights of a topographical map. And they have a special feature. Feature is they never end and they never cross, which is exactly what Smetics have to do. So that's good. By having, so now I can say, all right, instead of thinking about Smetics in 2 dimensions as these lines, I'm going to think about surfaces in 3 dimensions, mountain ranges, and I'm going to think about the structure of the mountain ranges. The structure of the mountain ranges is one-to-one correspondence with all the Smetics. And what's interesting about a mountain range, because, you know, the people here I know, they go to Aspen all the time, right, is you can tell whether there's a peak or a valley without going there by noticing, sorry?
That's not very here. That's not us.
I know, but I know that you know this. Well, let me, maybe not. Okay. The way you know that there's a peak or a basin is if you can walk around 360 degrees and never go up and down and come back to where you started. Right? Peaks and basins always end up to look like +1 defects, right? But if you were going from here to here, maybe you would go over Columbia Crest. Mike Cohn would go over Columbia Crest. Instead, you go over the passes. And the passes look exactly like negative defects. That's what that's a -1 disclination. And you say, well, so what? The so what is, there's a theorem, it's called the mountain pass theorem. When you have 2 mountains, there's always a mountain pass in between them. What that means is I can't bring 2 mountains together. I can't bring 2 +1s together. If I try to bring 2 +1 defects together, I will always have a pass in between them. Because of that, I can't have anything bigger than +1. However, I can have 12 mountains surrounding a single pass. Right? There could be this interesting pass where there are 12 mountains, and you can go into 12 different valleys if you want to, and you can have any negative charge you want. But you can't have any positive charge. And so what's good about that is now, by mapping our problem onto the problem of surfaces in 3 dimensions, we control the topology. We automatically get this constraint that you can't have bigger than +1. And then we start thinking more about it. So here are the edge dislocations. So here's the puzzle. Or puzzle. Question, isn't it? What's the surface look like for an edge dislocation? All right, I'm solving a topology problem, the 2-dimensional topology problem, by solving a 3-dimensional geometry problem. We did 2-dimensional topology, we mapped it to 3-dimensional geometry. What's the surface?
Cliff.
What?
Cliff.
Cliff? No. Here, I'll give you a hint. You go around once, and you go up by 2. The phase field changes by 2, and the phase field is the height function. So what kind of surface do you walk around 360 degrees and go up 2 layers? Not the bagel, the helicoid, the screw defect. So it turns out that edge dislocations in 2 dimensions come from a surface that's really a screw defect. It's really a helicoid. You may not believe me, so I made a picture. All right, so here's the helicoid. Far away from the defect, the layers are at a constant angle. Constant angle layers mean constant spacing of the ground state. The ground state of the Smetic in this language is just this plane at 45 degrees in any direction. See how it has the rotational symmetry and the translational symmetry? I can go up and down, and I can rotate it, and those give me the 2 modes. So now what I'm going to do is I'm going to cut the surface. I'm going to give you a cross-section of the surface. The cross-section is exactly what you see when you look at the level steps. So I'm coming down and get this black line. So far not so interesting. But there you go. Suddenly, there you can see the dislocation. Right? And you can even see how one type of dislocation turns into the other kind. Right? So a screw defect, or if you like a helicoid, in 3 dimensions, its sections look like an edge dislocation. They are in a dislocation. Okay. Now, it gets a little more complicated, but I wish there were a way of thinking about this with Fermi surfaces, but I don't know how. The Smetic has this n goes to minus n symmetry, right? So that's to say this direction and this direction are the same. It means that the ground state represented by this surface, see what I'm doing? I think the layers like this, is the same as the ground state represented by this surface. I get the same lines, right? Whether I tilt it like this or tilt it like that. So there's one set of geometries, tilted like this, there's another set like this. In other words, a peak and a basin can be turned into each other just by turning your map. 5 minutes, okay. So it turns out that you need to have both sets of surfaces when you have a disclination. When disclinations are there, disclinations change the phi to the minus phi. They change the up surfaces to the down surfaces. And so you actually have to consider a more complicated structure where you have two sets of surfaces, red surfaces and blue surfaces. And for instance, here is a half disclination, plus 1/2 disclination. This is what it looks like in 2 dimensions. But this is what it looks like in 3 dimensions. If you cut it on the top, you get this curve here. If you cut it on the bottom, you get the same curve. And then there's this line where the surface appears to intersect itself, just like the Klein Bottle appeared to intersect itself. And that's this line here. Here, so you see what it looks like? Yes. Okay. This is a minus 1/2 disclination. Here again is the top view. This one's harder to visualize. I don't know, it reminds me of that cartilage bone in a chicken. It does, right? So, I don't know if you can tell. So you have, here's the crossing, here's the top. Top gives you those layers, and then there's the bottom that you can see that also gives you those layers. And they cross through each other. Okay, it'd be like some gizmo, like some Lego set, okay, connected in 3 different directions together. So now I can look at something else that bothered me. I was telling somebody I was going to talk about this, and they said, well, disclination pairs. They're always dislocations. Who believes that? Raise your hand. Disclination pairs? Who's ever heard that? Nobody's even heard that? He's heard it. Right? Well, here's a disclination pair. Here's a plus 1/2, and here's a minus 1/2. But I can actually remove it. This is topologically trivial. It's called the pinch. Here's what it looks like in my 3-dimensional view. And I can just pull that little red nose back up into the blue blue nexus and make the whole thing disappear. 2 disclinations and cancel. Okay? Into 2 parts. But I can also write down a dislocation. Here's a charge 1 dislocation. And I can draw it in the same way. So now I have a minus 1/2 and a plus 1/2. There's a difference though. Not only is the difference that the red and the blue are in different places, but if you have the geometry in your head, and I'm sorry that I only have 1 day to get this to you, is, it usually takes a week, right? Is the red ones, the half and the minus 1/2, they come together at different heights. Right? So to get them to fit together, the red one has to actually be shifted down. Its line is not the same height as the line in the blue one. And I'll show you what I mean when I turn it sideways. See, to get them to fit, there's actually an offset between this line and that line. And what does that mean? It means that no matter what I do, I can't actually lift that red one up to cancel one of the legs or the arms of the blue ones. I can't move the layers up and down. I can't move the surfaces up and down. I can just distort them in the XY one. That's the topological rule. And I can separate them. So I can have deep disclination pairs that make deep dislocations, and I can have disclination pairs that don't. I can show you again the same thing. Here are the pairs making the dislocations. There's some energetic stuff. let me say the important index that I'll stick this part. You can ask yourself, can you make Smetic layers with constant spacing? And what topologies can you make, or geometries can you make things with constant spacing? Constant spacing means that the surface is always at the same angle to the z direction, the three-dimensional surface. Which means that if I look at the normal to the surface, it always lives here on this dashed line. Okay? Which means that it has no Gaussian curvature. You can calculate it. This surface has no Gaussian curvature if its normal always lies on this dashed line. And there's a theorem, it's an old theorem by Gauss, the theorem of Regium, that all surfaces that have zero Gaussian curvature are just the plane, or isometric to the plane. And there are three surfaces. There's the cone, there's the half cone attached to the plane, and there's a plane. And those correspond to the three defects that are known to be made, you can make with equal spacing. The +1, the +1/2, and the 0. All other defects must have non-equal spacing because they can't have vanishing Gaussian curvature. So let me go on. I showed you, this is the end. When I studied two-dimensional Smetics, instead of talking about homotopy theory, the right thing to do is look at maps from the plane to the surface, and I have extra symmetries. I have this surface, I have this surface, and so the surface is shifted up by 1. But that's just a mathematical nicety. I'm looking at graphs from the plane to the circle. And I get helicoids and X and phi are helicoids. They're the same structures, these two defects. How do I do it in 3 dimensions? Now I have to have graphs from R3, the three-dimensional space, to S1. And that'll give me things like the helicoid in space, which is the screw dislocation, or the helicoid in this other space, which is the edge dislocation. What about crystals? So has anyone ever been here? Does anyone know what this is? That's a person. That's a person, see? That's a real person. Standing on a real crystal. There are these caves in Mexico where they found these huge crystals in the gypsum.
Wow.
Right? They were underwater, and they were growing underwater, and then they were pumped out by a mining company. Right? So this area, this place is 110 Fahrenheit and 100% relative humidity. You can only explore it for maybe 5 or 10 minutes before you die. But if I want to study crystals, big ones or little ones, now I have to have graphs from R3, 3 dimensions, to the torus, those are the 3 periodicities of the crystal, modded out by one of the space groups of the crystal. So in principle, I know how to formulate the problem. Here are my summary, but I want to just show you that the first work was done with Chris, and the latter work, which appeared in PNAS, was done with this brilliant graduate student and this brilliant postdoc, Brian and Karen. So thanks for your attention.
I wonder if I add this functional a Hopster, and which which is going to give a sign or maybe a phase when I change to substantive location. I'm always wondering what is the statistical character if I were to do that with this dislocation.
So if you could add,
the
dislocations you could do it by doing gauge field.
Yeah.
But somehow the disclinations and dislocations don't enjoy that the right way. It's inappropriate to write things in that language as individual defects. Let me say it another way. You guys should have all jumped down my throats as soon as I talked about that two-dimensional ground state manifold, because you should have said there's only one Goldstone mode. How can the ground state manifold have 2 dimensions if there's only one Goldstone? And so that's the problem, that there's only one mode, this displacement mode. And I don't know how to couple it in general. I don't know how to represent the general orientation in that ground state manifold. So I don't know how to attach it. But if I did, it would be non-dealing. Yes?
You told us before that
disclinations can't fit together.
Oh, okay. Okay, then. It's too bad that they almost sound like the same.
So in terms of this presentation, how should we think about overlapping domains, or different sectors, where also you can have
So Ivan is asking about, in general, how do you study ecosystem structures? I guess we talked about it yesterday, the toric structure. So it turns out that those are sections of cones, right? And if I look at concentric circles with a +1 defect, I can say, oh, that's a cone. It just takes place like this. That's one defect. Now I have two defects. Those are two cones. And I look at the sections of two cones. When I do that, I get intersecting circles. And that will give me the two-dimensional focal cone. It turns out, we showed this, that in 3 dimensions is exactly the same. So then you have a 4-dimensional cone. And the intersection of 4-dimensional cones gives you all focal cones.
more questions? If not, let us thank our speaker again. And our next presentation will be given by Kamien, and she is from University of California, Davis. Her presentation will be on emergent structures in models of biological membranes. Let us welcome our speaker.
Well, it's a pleasure to be here. And in keeping with